whenever you are.
Okay. Well, I'll introduce you if that's okay. So welcome, everybody, both inside of Bell Labs and outside of Bell Labs. As a reminder, this call will be recorded. And as Sonia was just telling me, maybe you heard, it will be available slightly more broadly with our partners in Inria, which is exciting because we like working with outside people. So today we have Laurent Massoulié. Did I say that right?
Yes, that's right.
Perfect. My French is paying off. Okay, he's a research director at Inria. He's head of Microsoft Research Inria Joint Collaboration and a professor of Applied Math Center in École Polytechnique. And his research interests are right up our alley. So machine learning, probabilistic modeling, and algorithms, of course. And he's had numerous scientific positions and numerous best paper awards. We're extremely excited to hear him talk about optimization. So Laurent, over to you.
Thanks, Sean. Thanks for having me. It's a great pleasure to have the opportunity to give this seminar. So I'll be describing results obtained in collaboration with a bunch of colleagues of mine. I have put on the first slide the two archive papers that I'm going to borrow results from. And the first one is going to be an oral presentation at the forthcoming New RIPS conference. So let me get started. So the general context of what I want to tell you about today is that of federated learning or distributed learning. And my definition of federated learning would be that it's whenever agents pool resources together, and resources could be data, compute, or communication, in order to collaboratively solve learning tasks. There are a variety of tasks that can be envisioned. The most obvious one is supervised learning of a common model by all the agents. They seek one model that they will each use at their end. There are more refined or more complex objectives that can be envisioned. For instance, personalized learning. That's when agents will try to obtain a model that is more finely adjusted to their own data rather than to a common model shared by everyone. And finally, you could also envision unsupervised learning tasks. And agents could be operators of data centers, or they could be users of a smartphone. You have many scenarios that you can imagine. And you want to solve these learning tasks in a collaborative manner under some constraints. And there are obvious constraints like speed. You'd like to train your models as quickly as possible. Energy, you don't want to burn too many energy in the process. And privacy is another concern in those scenarios usually. So there is quite some momentum around these questions. And so I've put on the slide the front page of an archive paper that surveys many problems in this area and candidate solutions. And you can see that there are many institutions paying attention to that. And so this is an interesting survey that's not very old, so it's not yet outdated. And if you want to have a broader idea of the field, then you could have a look at this archive paper, for instance. So today I'll focus on a small subset of the issues of federated learning. I'll be interested mostly in the problem of a common model being trained by the agents together. And I'll be mostly concerned with speed and energy consumed in the process, and I will not pay attention at all to privacy, and I will not pay attention either to statistical accuracy of the model obtained, but rather I will focus on the optimization part of distributed or federated learning. So more specifically, I'll be discussing the problem of empirical risk minimization in a cooperative scenario. So let's introduce a bit of notation. Our agents, denoted by U, each hold a data set that is a personal data set. So D sub U is the data set of agent U, and it consists of a collection of data vectors, if you like. And so we have a loss function L, and as is traditional in supervised learning, we are going to try and solve the empirical risk minimization. Namely, we are going to try and find a vector X, so that's our model, in some d-dimensional space that minimizes the sum of losses evaluated on the individual data vectors and at the model vector X. And we sum this over all data sets of all agents. So that's the canonical problem, the simplest problem of distributed or federated learning, if you like. And so X star will be throughout the ideal minimizer of this empirical risk minimization. And so our game is to find this X star in a distributed setup as quickly or as cheaply as possible. All right, so essentially we are going to try and minimize the sum of functions, each individual function being associated with an agent, and it's the empirical risk of that particular agent for the model we are considering. So as I said, we'll be interested mostly on speed and energy consumption in the process. And in identifying algorithms that can bring us to the vicinity of the ideal model, the one minimizing the empirical risk at the cheapest and at the fastest, all right? So in the title, I highlighted the word asynchronous. The reason for that is that many of the known solutions and the best understood solutions tend to be synchronous. So there are rounds of computation, everyone proceeds in rounds. And synchronous setup is easier to understand and analyze. However, if you want to deploy that, you're clocked by the slowest agent in the system, and that can be painfully slow. So that's the reason why it's interesting to move to asynchronous methods. That being said, I will nevertheless start by telling you an awful lot about synchronous operation, because it's going to help us set the scene, introduce the key parameters, the network models, and also introduce a bit of background on optimization for those of you who are not experts in convex optimization. And so, for instance, we'll be able to talk about the notion of an accelerated convergence speed, which plays an important role in what I want to discuss. Then we'll move on to asynchronous methods and talk about accelerated gossip. And finally, I'll touch upon a scenario that is more challenging even than the basic asynchronous scenario. And that is a scenario where there are time delays between communications and computations performed by the agents, which is very realistic. And that happens in real life. But that tends to break all existing analyses. And so we'll see that we can salvage a number of results in that setup. Okay, and finally, I'll mention applications of all we'll have seen by then. All right, and please feel free to interrupt me as I proceed. All right, so let's introduce a setup for synchronous distributed optimization. For us, a graph will be used as a model of a network. So we'll have G comprising made of a set of vertices. Each vertex is an agent, and there's an edge between two agents if they can communicate directly between themselves. And we have attached to each vertex, that is to each agent, a convex function f sub u, and that corresponds to the empirical risk of that agent. And we want, as I said, to minimize the sum of the empirical risk functions over all agents. And so we'll distinguish two things that agents can do in this environment. They can, on the one hand, compute on their data. And for us, compute operations will be essentially computation of gradients. So they can evaluate a gradient of their local function at a given model. For those of you who know about convex conjugates, this is another function associated with the local function f sub u of agent u. And we'll assume also that agents can perform gradient computations on the convex conjugate of their local function. Okay, and so that's the compute primitive, and there's going to be a communication primitive, which essentially is exchanging vectors between neighbors in the graph. All right, so before I proceed, let me mention a special case. That's when the local functions are just quadratic functions, so the square of a distance between the current model X and the vector that is a property of the agent we consider. In that case, it's fairly easy to see that the optimizer is going to be the average over the local vectors. And so that's why this special case is called the network averaging problem. And it's been studied quite a bit in distributed computing literature. One of the reasons for that is that, for instance, it's a useful primitive if you are in an environment that you don't know too well, and you don't even know how many agents there are out there. Then you can start a computation where one agent, say U0, starts with value 1, the others start with value 0, and they say, okay, let's compute the average of our values, our private values. And now this average will turn out to be 1 over the number of agents in the system, and so everyone gets to learn the size of the system. So that's a digression, but that's why in distributed computing, this problem has received a lot of attention. All right, so to complete my description of the setup for synchronous optimization, we'll have tau comp denote the number of time units to perform one compute operation, and tau com the number of time units to perform a communication step. And so we'll assume operation in rounds. In one round, each agent computes something and then exchanges something with its neighbors, and that's about it. All right. Okay, so we'll further specify how communication happens in that setup. We'll assume that when an agent communicates with its neighbors, it receives a linear combination of input vectors of its neighbors, and so there is a matrix. Here it's denoted L, which says which combination of the inputs of its neighbors it gets to receive. So that's the equation in blue here. And so we have some properties of that matrix that specifies communication. It's symmetric, it's positive definite, semi-definite. Its null space consists of constant vectors, and it has non-zero entries only when two neighbors corresponding to that entry, two nodes or agents are neighbors in the communication graph. All right, so that's the setup. And for us, we will always use the same matrix, which is a classical construct in graph theory, which is the Laplacian matrix of the graph, which is as specified on the slide. Or we'll also need to consider a slight generalization of the Laplacian, which is a weighted Laplacian, where we introduce weights on the edges of the graph. All right. So that's how we are going to perform communication steps using this gossip matrix, which turns out to be this Laplacian, and we'll have computation steps in between. Okay, so to proceed, let me describe some parameters capturing the hardness of communicating in that environment and of computing a minimum of the convex functions that we are dealing with. So complexity of communication is captured by specific properties of the Laplacian matrix L. And so this Laplacian matrix has eigenvalues and that are non-negative because this is a positive semi-definite matrix. And so we'll measure the hardness of communication by the condition number of that matrix, which happens to be the ratio of the largest to second smallest eigenvalue. And so as an example, if you look at the complete graph, that's when you can talk directly to anyone in the system, then this condition number is 1, and that means it's an easy scenario. Whereas if you take a cycle, then your condition number turns out to be on the order of the square of the number of agents in the system. So that blows up quite fast if you are dealing with a large system. And so that's a much more challenging scenario than the complete graph. Okay, and I need as well to introduce complexity parameters for the compute part of our problem. And these are assumptions that are very standard in convex optimization theory, but we need to spell them out nevertheless. So we'll characterize the hardness of optimizing our functions by two parameters, alpha and beta. And basically, the matrix of second-order derivatives of our functions. So these are lower bounded by alpha and upper bounded by beta. So we have a bracketing of these matrices of second-order derivatives. And now the ratio beta over alpha is our condition number for the optimization part. And the higher it is, the harder it is to optimize. All right. Okay, and so in the special case of network averaging, alpha equals beta equals 1, so that's very easy in terms of optimization. That can be hard in terms of the network, though. Okay,
question?
Yep.
When you say optimize, you mean the speed of convergence?
Yes,
Okay.
Yeah. I want to optimize these functions at an optimal speed. So I want to optimize the optimization process in a sense.
So how fast does the iterative scheme converges?
Yes. I want to get in the vicinity of the optimizer as quickly as possible. That's the game. As quickly and as cheaply.
Thank you.
You're welcome. Okay, so I had this slide, which I think I'm probably gonna skip because this is for those who are familiar with the convex optimization theory. So there's a dual formulation that makes the problem that looks very complex turn out to be very simple and actually a special case of the standard theory of a convex optimization. But let me not dwell on that. Let me skip the particular construction of the dual problem. And let me just describe a first scheme. And as I skipped the details, but basically this is a gradient descent on a convex function. It turns out to be a dual convex function, but that's basically gradient descent. And so that's the top line here. And so that's what you get to learn in the first chapter in a convex optimization. This is optimization 101, if you like. All right, and so if you've read the first chapter of your favorite convex optimization textbook, then you'll learn that the speed at which you approach the optimum using this gradient descent is exponentially fast, but there is a critical time constant, and this critical time constant is the condition number of your problem. And in that particular case, the condition number will be the condition number of the functions, kappa comp, times the condition number of the network, kappa comp. So we can expect to get to the vicinity of the optimum in time that is proportional to the duration of one iteration, so tau comp plus tau com, number of steps we need to compute and number of steps we need to communicate, and we multiply that by the condition number. All right, so that's optimization 101. Now, if you move to the second chapter in your favorite textbook in convex optimization, you hear that you can accelerate convex optimization, and there's this beautiful thing which is the Nesterov-acceleration, which is a momentum-based approach. So instead of just doing gradient descent, you tweak, you get two sequences, and you can think of one as being the acceleration and the other the speed, and you set the acceleration of your dynamics to the gradient gradient of your function. So it's a second-order scheme or momentum-based scheme, and so this can be written very simply. These are the two equations on that slide. And the benefit that you get from doing this trick, this Nesterov-acceleration, is that now you apply a square root to the condition number. But apart from that, you get the same kind of convergence result. So, and when you don't know about convex optimization, you think, well, this is not really a big deal. I mean, they just threw in a square root. But it does matter an awful lot in practice. And so, for instance, if you take a cycle network with 100 nodes, we've seen that the condition number for the network is 100 squared. And so now a square root gives you back 2 orders of magnitude in the speed to converge. So that does matter quite a lot, in fact, in practice. And so I want to throw in yet another result in this synchronous approach. You might ask, okay, this is good. There's an upper bound on the convergence speed. Now, can we get much better than that? And we can get a bit better. And so this is what I want to tell you about just now. So I've described you something where each time you communicate, you compute. So you tie in communication and computation, and you don't need to do that, in fact. You can, if your communication graph is hard, then you're better off by doing several steps of communication before you do a step of computation. And so that's what I'm describing here. So there's a specific way that you can do several steps of communication, which amounts to replace your Laplacian matrix by a polynomial of this Laplacian matrix. And so there's a specific polynomial that you want to use that happens to be the Tchebitchev polynomial, which is another landmark of optimization theory. And so the magic of the Tchebitchev polynomial allows you, if you do the right number of communication steps, to implement the polynomial of this Laplacian matrix instead of the Laplacian matrix as your gossip matrix. And then you do a gradient step. Then the same theory I've described up to now gives you a result that is slightly better with decoupled communication and computation. And so the square root of the kappa com only multiplies the delay in communication and not the delay in computation. Okay, so that, again, what's the big deal? Well, the big deal is that you cannot do better than that in general. So that's as good as it gets if you do synchronized operation. So that's something we've established in a paper in ICML 2017. So that, in a sense, I wanted to get to that result to illustrate the fact that we do understand quite well by now the synchronous scenario, and we understand other twists that we might want to do. We can introduce stochastic gradient descent operations if we don't want to compute a full gradient at each agent. We can do a number of twists like that. So this is well understood. The asynchronous situation, however, is far less understood, and so this is why we are happy that we could get results in the asynchronous case.
Just to check, I'm okay. So this is good if the computation time is far greater than the communication time, I guess.
Well, typically this matters if your network is like a ring, so not too good. So the kappa comp is high. So you don't want to do too many computations. And that's good in any case. You save on time and you save on energy. So maybe you save a little, but you save. So. Okay, so let's see what we can do in an asynchronous scenario. So let's introduce a model for asynchronous operations. It will be very convenient for us to assume that the asynchronous operations, which amount to two neighbors interacting irrespective of what the rest of the system does, occur at random times. For us, these will be Poisson processes. And so for two neighbors U and V, we'll denote by P, U, V, the frequency with which these random interactions between U and V occur. Okay. So for us, the modified hardness parameter for the communication is now 1 over lambda 2 of the Laplacian matrix of the graph. where we weigh now the entries of this Laplacian matrix by those frequencies. Okay, so that's the analysis tells us this is what we should do. And so now we have a scheme that is as simple in a sense as the one we described previously in the synchronous scenario. Whenever two neighbors U and V interact, then they do some kind of a dual gradient update as written here. And so we can analyze that reasonably easily, and we get what we expect, namely that we approach the optimum at a rate that is determined by the product of the condition numbers we have. So the kappa comp is unchanged, then we have this slightly modified kappa com involved. Okay, so that's a simple enough analysis. Can we accelerate that? So that's what took us quite some time. And in fact, it was not known before if there was a standard acceleration procedure that could get you accelerated rates for this kind of problems for an arbitrary network. And so, yes, we can. And we can do something like Nesterov-acceleration, but it's not quite the textbook Nesterov-acceleration. So as in Nesterov-acceleration or in momentum-based methods, we need now agents to maintain not one, but two vectors, all right? We have discrete updates in our scheme where upon activation of an edge between U and V, well, they exchange gradients and update their variables. But in between, we have what we call the continuous mixing between the individual variables of each agent. So conceptually, they let their vectors evolve according to an ordinary differential equation and a simple one, linear one, as I've written here. Okay, so this is a scheme that's described in this manner, and we do get accelerated rates. So the critical time for convergence is the square root of what we had if we did not introduce this second set of vectors y sub v for each agent. Okay, so a few comments on that result. I've described it in the conceptual manner in which we analyze it using ordinary differential equations. You don't want to implement that. You can just at the time where you do an update, you solve for what is the endpoint of this ODE by the end of the interval, which is straightforward given the simplicity of these ODEs. So the big deal is that there is no synchronization step. It's just two agents decide to interact, and so they do. A catch is, well, we think it's not a catch, but there is an underlying assumption to have our result, which is that the clocks of the agents are synchronized. We want, when we solve the ODE, it doesn't matter how long has elapsed between the previous update and the current update. And so the logic of the scheme that we analyze assumes that each agent has a clock that is synchronized with other agents' clocks. So the third point here is that, in fact, we realize that what we have here is a new variation on Nesterov's acceleration scheme, which is fundamentally different. And so that adds to the toolkit of the convex optimization practitioner. And that's one of the key results in the archive paper I was displaying on the front page. Okay, and so last point is it does matter in practice because, as I said, acceleration does matter. If your network is bad, then you do want to accelerate. This will buy you a lot of time. Okay, the practice is in agreement with the theory. That's what this slide means. You see a network averaging with and without acceleration in this asynchronous setup, and so the green curve is with acceleration and it goes to zero, your optimization error at a faster exponential rate than without acceleration. So let me not dwell on that. And I don't know how much time I have left.
Say 25 minutes.
Oh, okay, okay. So I need to speak slower then. Okay, well, that should be all right. That should be all right.
There will be questions afterwards. No
Okay,
no.
okay. So let me move on now to the last thing I wanted to discuss, which is how to handle time delays in our system. So here's our model of that and the algorithm we are going to consider in that setup. We'll again assume that we activate operations at random times. That's very convenient, but that's an algorithmic design choice that we make. You can really do that. It's not an assumption, it's a design choice. So we'll assume that each agent triggers compute updates at random times with a Poisson random times, and P sub u will be the compute update frequency for agent u. Is there a question? No? Okay. And we'll assume that there's a delay. When agent u starts a computation, it takes at most some time tau sub u. Okay, it could be small, it could be large. We could have stragglers, nodes that take forever to compute, and we could have nodes that are very fast. The whole point is to allow for heterogeneous delays in this part. For communication, again, we assume that communication between two neighbors happen at random times. So we have a Poisson process of communication updates between two neighbors. And so between u and v, P sub uv will be the frequency of that process. And we have some delays as well for communication. We assume that whenever agents u and v decide to interact, they complete their exchange by some time at most tau sub uv. And again, we want to allow for heterogeneity with slow links, fast links in our network. Okay. So how about the logic of the updates that these agents perform? So we'll assume that they maintain two vectors each, so x sub u, y sub u for agent u. And so communication updates first. These are going to be as described in the equation. So assume that at some time t minus tau sub u v, agents u and v decide to interact. So at that time, t minus tau sub u v, they know about their vectors xu, yu, xv, yv for that current time. But then the interaction will complete sometime later. And so the logic we adopt for this interaction is that they do an additive update at the current value of their x vector, tau sub u v seconds after the interaction was initiated, and the amount by which they increase their vector at that time t is computed based on what was available at the time they decided to interact. So that's the key point of that equation. This is something that you can do in the presence of delays in your system. For compute updates, we have a similar kind of logic. That it's a bit nastier because I need to introduce a modified convex function, but don't worry about that. We compute a gradient on something. And so when we decide to do a compute update at a node u, we can do that independently of any communication updates. Everything is decorrelated. It's very modular. And so at time t minus tau sub u, the agent computes some gradient, stores the current value, and sometime later, the gradient computation has completed, and it can do some additive update to its local variables. So that logically, that can be performed even in the presence of computation delays. And so importantly, when we do these updates, the compute and the communication ones, there are gains in front of the additive updates. So let me return to the communication updates. So at the frequency PUV, you do an additive update on your variables. And so the constant in front is KUV over PUV. So essentially, the magnitude of the updates per second is driven by KUV. And so that's what we call the gain of these updates. And similarly, for compute updates, you have a gain KU, which is the magnitude of the updates on average per second performed for computation. So it's well known in time. Yeah. Okay. It's well known when you are dealing with systems with time delays, and we try to control them based on a delayed feedback, that you cannot tweak them and control them to the desired equilibrium as quickly as you like. Otherwise, you will incur oscillations. And so that's something that I guess you all experienced when trying to tweak the shower temperature to, say, 40 degrees. And if you try to do that too fast, you'll alternate between too hot and too cold. So that's a fact of life. So we have constraints here. We have something to pay. There's no way around that. And so to us, the conditions that we impose are as on the slide. So let me not read them, but intuitively, for the shower example, you cannot have a gain that is much larger than the reciprocal of the feedback delay between the time you turn the knob and the time you feel the impact on the temperature. So that's the typical thing in delayed systems. You need to your gain the reciprocal of the delay in the feedback loop. And so that's what happens on those equations as well. If you look at, say, the bound on KU, you will see at the bottom tau u on the denominator. And so that's the manifestation of this property of time delayed systems. We need that in order to ensure that we are going to converge at all to the optimum. Okay, so how fast are we going to converge? We want now to introduce new parameter that is the second smallest eigenvalue, lambda2, of a Laplacian that is weighted by those gains k that we have tweaked according to this equation A above. And so the result we get is as follows. We have convergence, exponentially fast convergence, provided we meet the conditions A. And we have a critical time for convergence that is the maximum of three things. So there's one that you cannot avoid. This is this tau max. The critical time has to be at least as large as the largest delay in the system. There's no way around that. The last term deals with compute updates. And the first one is the most interesting one. This is the one that bundles communication and computations together. And so communication is captured by a single parameter, which is the second smallest eigenvalue, lambda2 of the k-weighted Laplacian. Okay. Some comments about this scheme. It can be implemented in an event-driven fashion, so no synchronization steps. It's asynchronous, we claim. Again, for the analysis to carry through, we need the clocks of each agent to be synchronized. We need them to agree on at which time a decision to interact was made. And so if their clocks are not synchronized, you cannot do that straightforwardly. But okay, with modern machinery and network time protocols and the like, that seems like an okay assumption to make. Second comment is that we capture with this kind of operation what we call the asynchronous speedup, namely when we have fairly heterogeneous delays in communication or in computation across the system. Then we get a big advantage compared to a synchronous approach where we would clock everything at the largest delay in the system, because well, the way those delays appear is through the second smallest eigenvalue of this K matrix. And so that's intuitively, you can think of the gains K sub UV as on the order of 1 over the delay tau UV. And so this is the individual delay, not the worst case delay. And so this lambda 2K can be much larger than if you were using the largest delay in the system. And finally, condition A can be rephrased in a simpler manner. It's basically equivalent to saying the spectral radius of a matrix that I won't care to write down is less than 1 for a matrix depending on the gains K. So implications, if we want to maximize the speed for a given network, then because of this characterization of condition A, we can just say I'm going to maximize the second smallest eigenvalue of the k-weighted Laplacian over parameters k, such that the spectral radius of a matrix linear in k is less than 1. And this is a convex problem. So this is a convex constraint, a concave objective, or linear. Yes, concave objective. So this is a concave maximization problem, and this can be solved efficiently. So we can, in this setup, do this optimization and easily get the best gains and get the fastest convergence given a scenario with delays and so forth. Another thing to take away from this result is that if we, so I talked about speed only so far, but as I mentioned earlier, we are also interested in the energy consumption as we do our collaborative learning. And so a natural assumption to make is that the energy consumption in this particular scheme is proportional to the frequencies at which you do updates. So one communication might cost a bit of energy, one computation might cost a bit of energy. So we would have something that is an energy cost proportional to these p values. And so this justifies trying to optimize something like the expression in blue at the bottom of the slide, namely maximize something that is that captures the speed at which we realize the optimization minus the energy consumption per time unit. Okay, and so we may tweak the relative importance we give to speed or to energy consumption by tweaking this omega parameter in this expression. So now this is a much more complicated optimization to do. It's not a convex optimization, but we can solve it offline and tweak our pipeline for solving for solving our collaborative optimizations offline. And so we've played a bit with that, and it was not something we were seeking initially, but we came across an intriguing paradox that is reminiscent of the Braess paradox that I guess many of you know about. So for those who don't, Braess paradox says that in a road network, if you remove a road, you can make the traffic flow much more rapidly. And okay, so less transmission capacity makes for a better network, at least for road traffic. And so for optimization, we have something a bit like that. So on this picture, you have at the top two networks which come with communication delays. And we assume initially that the frequency with which we use those links, the P sub UV, are tweaked to the reciprocals of the delays. They are set to 1 over tau sub UV, okay, which is like what common wisdom advocates for. Okay, so that's what we start for and from, and then we run the optimization I was describing in the previous slide. So we modify the P parameters so as to maximize this objective function here. And as a result, what we find is that we arrive at networks where we have removed edges. And we have modified the frequencies with which we use the edges. and optimization is faster and energy consumption is lower. So we gain on all sides. So we use less links, we converge faster, and we consume less energy. So there is scope for tweaking those schemes and to get a significant advantage.
Is the intuition that you removed the slow links, or is it much less?
We do that. Yes. It has a strong impact removing slow links. For instance, if you have a ring with say 1 kilometer distance between neighbors, and then at the two ends you have a very long link, you want to suppress this one. This is killing you, in fact. So
and the line is better.
The line is better in that case. Exactly. So we have, a black box optimization, which tells us, okay, remove that link, increase the intensity with which you use this one, and so on and so forth. Yeah. Okay, so I'm reaching my last slide. So as a conclusion, we have simple asynchronous schemes that only require synchronized clocks. So we don't have a completely asynchronous setup. We just have synchronized clocks. But that's okay, we believe. The accelerated scheme in the asynchronous setup that I described, that was the first asynchronous solution to network averaging problem that would provably accelerate for any network. In fact, there were interesting results by Alex Dimakis from UT Austin a couple of years back on grids or on networks with a strong geographical structure. And so he would use what he called geographic gossip. Actually, we could somehow have a solution that works for any network, no matter what the geographic or non-geographic structure is. Okay, so last things I was describing, I'd like to re-express in this way. For the delay tolerance scenario, our results give us engineering rules, you might say, to perform network sparsification and to actually tune properly the schemes. And okay, so there's this Braess-like paradox, which is still intriguing to us. We don't fully understand it, even though, okay, on the cycle, this is the example we do understand, but in general, what drives that is a bit more mysterious. And so as future work, we are yet to see how to combine acceleration and delay tolerance. So the two models I was describing, we have not yet something that accelerates in the presence of delays. And it's not clear it's easy to do. Well, it's clear it's not easy to do, rather. Okay, and so we believe that the speed guarantees we get are unimprovable in some sense, up to acceleration. Empirically, we verified this, but okay, this is a partial empirical verification. We don't know for sure. All right, thanks for your attention, and I'm happy to take any questions you have.
Thank you.
Yes, thank you very much. That was excellent. Perhaps since we have a on-site presence and a virtual presence, maybe we could start with the on-site presence. Fabienne, I don't know if there's any questions from people there.
So maybe I can start because I've got one question.
Mm-hmm.
If I get it right, your graph is not directed.
Undirected, yes, that's right.
So I've got two follow-up questions, obviously. First one, what happens if you're bidirectional, but not necessarily with the same delays and things like that? Because I see from the formula that there was a kind of symmetry in the exchange to make it happen. And so if your delays and costs are not the same, is it easy to patch or not?
So I guess the natural patch is when I was saying tau UV describes the delay for interaction, that was the back and forth delay. So if you have a physical communication delay in one direction and another one in the other direction, I think our model could be applied by setting tau UV to the sum of those two individual delays. If you don't have a return path, then okay, that's...
That was actually the second question. What happens if you've got a strongly connected directed graph, but with no guarantee that you can return? You can just send some data to one node, but you can't say what it will do with that.
So that's a very good question. So our theory breaks, that's for sure. And we know that we could expect good results even if we have asymmetric or directed graphs. So that there are optimization schemes where you have a message that travels the network and accrues information as it goes, and does not backtrack. It does not. It wants to visit the nodes as fast as possible, so it does not want to use the symmetry of the edges.
Actually, for some optical rings, it is possible, but physically, this is what you want to do to optimize the bandwidth to just follow the ring in one direction.
Okay. So we have not really thought about it, but okay, that's a very good question. Yeah.
Do you have other questions? No, we can go virtual if you want.
Go virtual. So thank you. Are there any questions? People who are virtual?
I have one question. This is Matthew Andrews. Thank you very much for the interesting talk. One thing I was curious about is whether there's any work to try and make schemes like this invisible to the end user. So if I want to use normal gradient descent, I can just use PyTorch and all the details of the algorithm are somehow hidden from me as a user. I was just wondering, for these type of distributed schemes, are there efforts, say, to allow you to just kind of define a peer-to-peer network of agents, and that would then allow one to kind of implement these schemes in a way that the user is kind of doesn't have to worry about them? Or do you think it will always require some handcrafting from the end user?
That's a very good question. I had not thought about it at all. And so I'm not sure I will make sense trying to answer it. It seems to me that the logic of our schemes could be hidden quite a bit. So I think there is scope for doing what you suggest, and that we may not need to go very far from the schemes we already have. Yeah, maybe I'm mistaken, but that's my impression off the top of my head. I think that that's doable.
Okay, thank you.
Any other questions?
I have a question. Is there an actual model in which the edges appear and disappear, or is that just the idealization that is interesting?
So what I described to you is really assuming we have stable links, and so I guess that's okay if you're talking about agents that are data centers, for instance. And okay, optimization training of a model of data that sits in several data centers and data that is so huge that you don't want to centralize it in a single data center. These scenarios exist, so I think our assumption of stable links is relevant to such scenarios. But of course, if we go to, say, smartphones, data sitting on smartphones, we have links that are not stable and they may disappear for a long time. Or so there's a significant effort in the area, and so that's the reason why I wanted to show you this survey on federated learning. So I know of some works trying to deal with varying networks. And there are various ways in which this is done. So, for instance, there are researchers who assume that links go on and off according to a stochastic process, and that they know this stochastic process. And then you can have guarantees for distributed optimization over a time-varying network where the time variability is through some on-off, stochastic process. There are other lines of works where people look at what they call time-varying networks as well, but where they make assumptions like if I take the adjacency matrix of my graph at time t, then at t plus 1, etc., until t plus d, then altogether I massage those d adjacency matrices together, and I have guarantees on the fact that I can communicate between two nodes in d time units. And so that they have some constraints, like a Laplacian of a composed matrix involving the d time steps has to have a spectral gap that is at least some lambda 2, and they can unroll some theory for that. Whether the first kind of assumption or the second kind of assumption is relevant to, say, the scenario of smartphones, I'm not sure. I think we may not have seen yet the right way to capture unstable or highly variable environments.
So would you say that the simple stochastic gradient that Matthew was referring to in a federated learning setting would be a good example for your model, or not?
Well, it depends on, okay, so we can really apply as is our method if we have stable links. So the example, so it's not a property of what you hide from the user, it's a property of the stability of the collection of agents, their data sets, and the connections between them. So if this is stable, then yes, we can, that's a good example.
Yeah, but there are examples of federated learning where the different communities are not always connected,
Mm-hmm.
So, yeah. Okay, thank you.
You're welcome.
Excellent. Well, thank you very much for the excellent talk, for your time coming and speaking to us. We appreciate it. And thanks everyone for all your questions and your engagement. And we'll see you next time, I suppose.
Thank you, Laurent.
Thank you.